So this is our last lecture today on duality and optimality. And we're going to try to bring it all together in the sense that we're going to try to talk about some of the uses and the correspondences in dual problems. So the goal is that after this unit's over, you'll have the tools that you need to derive dual problems, and you also have a hunch for when that would be a good idea to try to derive the dual. And finally, you'll be able to recognize situations in which you can derive the dual, solve it, and then get a primal solution from the dual. So we're going to wrap up duality today. Just a preview of what's coming up. Next unit is our second order algorithms unit. So we talked about first order algorithms, first order methods already. We'll talk about second order methods next. After we finish with second order methods, we'll have done 2 algorithms and 2 theory units. That'll constitute kind of like all the basic, I call it fundamental material of the course. So that's the stuff that I think you should, any person taking optimization should know in those first 2 units. Then we'll have our midterm after that. It'll cover the first 2 algorithms units and the first 2 theory units. After that, after you guys get that all out of your system, you become masters of kind of the fundamentals, we'll talk about advanced topics. So we'll move to things after that that are more recent. We'll probably pick and choose some things you find interesting. And I may take a survey at that point to see what it is you guys want to hear. Let's see. In terms of a few administrative things, I think you guys should have gotten back feedback from your project proposals. Most of the TAs have delivered the feedback already. If not, then your TA mentor will do so very soon. So that the projects should be underway. The homework you have, next homework is due on, I think it's next week. Is it next Wednesday? It's a week from today. Any questions before we start today? Okay, so let's jump into this last lecture on duality. So last time we talked about the KKT conditions. That was our last lecture. And remember that these applied to a general problem. You wrote down this problem in its most general form. Need not be convex in kind of the most general case. Right, we just have criterion, inequality constraints, and equality constraints. The KKT conditions are a set of conditions that apply to the primal variable x and dual variables that are defined for each constraint. So we have one UI defined for each inequality constraint, one VJ defined for each equality constraint. So the KKT conditions are conditions on x, u, and v all together. And they are stationarity, which says that if we form what's called the Lagrangian, and we take a subgradient of that quantity with respect to x, then we should have 0 as a subgradient. It's called the stationarity condition. It means that x minimizes the Lagrangian right at the pair uv. Complementary slackness said that the dual variable you introduce for the inequality constraints has to either be 0 or the corresponding inequality constraint has to be itself tight. We have to have hi of x equal to 0. And then the last 2 sets of conditions are just feasibility conditions. The value of x we're looking at has to be feasible, and the value of u we're looking at for the dual has to be bigger than or equal to 0 in each component. Those are just primal and dual feasibility. If x, u, and v satisfy these conditions, then we know always, for a convex problem or not, this implies that x is primal optimal and u and v are dual optimal. That is something we proved last time. These are always sufficient for optimality. Furthermore, if we have a situation in which we know strong duality holds, which means that there's no duality gap, the primal at its optimal value and the dual at its optimal value are equal, then we know these are also necessary for optimality. So under the kind of problem class we care about most, which is convex problems for which strong duality holds, right? Remember, Slater's condition told us that for convex problems, if there's a strictly feasible point in the primal, then we get strong duality. So for that class of problems, then the KKT conditions are necessary and sufficient for optimality. So they completely characterize what it means for point x to be primal optimal and simultaneously what it means for the pair UV to be dual optimal. We also kind of hinted at before, along the way, two key uses of duality. And I'll just remind you what they were. The first is an algorithmic concern. So this is something that's important when we're actually implementing algorithms. Say a first-order method, like the methods we've learned so far. Suppose we were able to derive the dual, and we're performing, say something like gradient descent or projected gradient descent or proximal gradient descent, one of our methods we know so far, on the primal as well as the dual. We keep a track of x, we keep track of uv, and we iterate the primal variable x with respect to its primal problem, and we iterate uv with respect to their dual problem. We try to solve them both, and so we're minimizing the criterion f, and we're trying to maximize the criterion g. And what happens is we get to a point where we check that the achieved value of f of x minus the achieved value of guv is less than or equal to, say, 0.01. Well, that implies that actually f of x is no farther than 0.01 from its optimal value, and guv is no farther than 0.01 from its optimal value. So the duality gap is a bound on the suboptimality that we're seeing at each of those iterates. That comes because guv is always forms a lower bound on the primal optimal value f star. So if we subtract off f star from f, that's going to be no bigger than the difference between f of x minus guv. And the analogous argument applies to g, right, that says that guv minus g star is also no bigger than this quantity. Or actually, in that case, it would be g star minus guv, because we're trying to maximize the dual problem. So in summary, the duality gap is a bound for both the suboptimality we're seeing in the primal and in the dual. So that can be very useful as an algorithmic stopping criterion. So it's our first example of an implementable stopping criterion. It doesn't depend on unknown quantities that will give us a guaranteed distance from optimality if we were to stop it at a certain level epsilon. Another important use of duality is not an algorithmic one, but it's I guess it is maybe ultimately can be an algorithmic one, but it starts off as just as a mathematical observation, which is that under strong duality, we know that the KKT conditions are necessary and sufficient. And the first KKT condition tells us that, right, the stationarity condition says that 0 is a subgradient of f of x plus the sum of ui subgradient of, I guess I call that h I of x plus the sum of vj subgradient of lj of x. This is the same thing as saying as x minimizes the Lagrangian Lxuv. And therefore, if we go ahead and we compute the dual solution, if we derive the dual and we compute the dual solution, then this forms a characterization for the primal solution. So this characterizes the optimal x, the primal solution, in terms of the optimal uv. This is going to give us a way, in many instances, give us a way to compute a primal solution from a dual solution. Okay. Any questions about these uses? So let's jump ahead to the second point and see when we can solve the primal problem via the dual. So if we were lucky enough to have found the dual solutions, suppose we derived the dual, we knew that strong duality held because our problem in the primal was convex and had strictly feasible points. And then we tried to use this fact, that x minimized the Lagrangian. If we were to plug in the dual solution, uv, the primal solution x would be characterized by the minimizer of this Lagrangian. So unfortunately, right, if let's suppose that we were to write down, there's two cases we can think about. So the first case we can think about is when the minimum over all x of L x uv is non-unique. Right, so let's suppose that there's more than one point x that minimizes the Lagrangian at u and v. Well, that's not, in this case, we're not going to actually be told an explicit form for x, because all we know is that x is a minimizer of the Lagrangian. We don't know which one it is. The KKT conditions tell us that x must minimize the Lagrangian if we stick in the optimal u and v, but we don't know which one of the minimizers it is. Here's a let me ask you guys just a thought experiment. If I told you a convex problem had a non-unique solution, how many solutions must it have? What was the answer? Infinitely many. Why is it infinitely many? Because the solution set's convex, right? So the solution set of a convex problem we know is always convex. If it has 1 point, it's unique. If it has more than 1 point, then, for example, if it has 2 points, then any point along the line segment joining those 2 points we know is also a solution. So it's not only infinite, it's actually uncountably infinite. It's a very, very large set. So in general, if it's non-unique, there's going to be infinitely many solutions. We don't actually know which one it is. But this can be still used to characterize the primal solutions. It still characterizes the primal x, because we know that at least if we have some form, right, for the set of solutions, then that form also will apply to x. So we'll see, I think, an example of that in this lecture. Okay, the second case we should think about is when the minimizer is unique. This pencil is giving me trouble. Right, in that case, actually, we know that this determines the primal solution exactly. Because if x minimizes the Lagrangian at the optimal dual u and v, and there's only one solution, then that must be x. So this is the case that we hope for more often in practice, right? We actually would like to know an explicit form for the primal solution. So this is really the case we're hoping for. But this case can still happen, the first case. This is a very useful observation when the dual is easier to solve than the primal, right? If the dual is easier to solve than the primal, then we've transformed our primal problem into an easier one. We've solved the dual. And if we end up in the second case, that means that we can recover the primal solution at less of an effort than it would have taken to solve the primal in the first place. So when would the dual be easier to solve than the primal? We'll see a few examples of that today. There are some general principles that I'll mention out loud and we'll get to in detail. But remember, we know that the dual problem always has dimension equal to the number of primal constraints. So if there's few constraints in the primal, but the problem dimension is very large, right? If the problem dimension is like 1,000 and there's only, say, 20 constraints, then if we could derive the dual, it would be a 20-dimensional problem instead of a 1,000-dimensional one. So that would be, in many cases, easier to solve. Another thing we're going to learn is a trick called dual decomposition. And you're going to see that in your homework too, although it's kind of hidden on your homework. If we have a linear transformation in the dual, if you have a linear transformation in the primal, and it's being applied in kind of an unfavorable place, like suppose we have some function g of a linear transformation of x, g of a of x, then if g is non-smooth, it might be hard to deal with that term, because maybe we're trying to use the prox operator of g in some way, and we don't know the approximator of g composed with a. Or maybe that's a constraint. Maybe g is an indicator function, so it's saying that ax has to lie in some set. These are often hard things to deal with. By deriving the dual, we can shift the transformation out of G into another function in the criterion. So that's something you're going to see on the homework. We're going to see it in this lecture. So we can often interchange the role of the linear transformation from being maybe convolved with or composed with a non-smooth part in the primal to a smooth part in the dual. We'll spend a whole lecture on that later in the course when we talk about dual methods, dual decomposition. This is the basis for example, for ADMM, the alternating direction method of multipliers. But we'll see some examples today as well. So let's get to an example where you're going to see exactly the concept I just talked about last. We're going to take a constraint that's kind of annoying in the primal because it's tying together all the variables. And we're going to see in the dual that it separates out. So we're looking at this general problem form that I have on the slide, which is minimize the sum of fi of xi subject to A transpose x equals b. Now, if I didn't have this constraint, I would be in good shape because actually I could solve each of these. I could minimize each of fi individually, right? Because fi only depends on xi, so this would decouple into n minimizations, right? There's no complication here. This would be n univariate minimizations. But this constraint is what prevents me from doing so. It's tying together these functions in an annoying way. I can't just kind of go out and minimize fi of xi individually because I have to pay attention to what happens to fj of xj because of this constraint, A transpose x equals b. And let's assume, just for simplicity, that each fi is smooth and it's strictly convex. So this thing is differentiable and it's also strictly convex. That's just for simplicity. Let's derive the dual function, the Lagrange dual function. So remember, the dual function, right, is given by, it's first of all a function of only one variable here. It's very nice because look, I have one constraint. So the dual is going to be one-dimensional minimization problem, and it's given by minimizing the Lagrangian over all x. What's the Lagrangian, right? It's just equal to the criterion plus v times A transpose x minus b. Just adding this equality constraint with a Lagrange multiplier. What's the nice thing about this? This problem now decomposes into n separate minimizations. Right? Let's write this out. This is the minimum over all x of the sum over all I of fi of xi plus v times ai xi minus b. Or I suppose we would want to write minus b over n. Well, actually, since it's a minimum over x, we actually don't care about that term. Right? That term's just going to stick around. So that term will be here, minus b times v. Okay, so look at this minimization problem that we have to perform over x in the Lagrangian to get the dual function GUV. It decouples into n separate ones. So in many instances, we can analytically solve this if f was a nice function. We've kind of already gotten rid of the role of the constraint. We're going to see in a few slides that this is exactly, I suppose actually up here, just for convenience, it wouldn't have mattered, but in the slide I have it written as b minus A transpose x. It doesn't matter. The dual would have been equivalent in either way, but it's just more convenient. We're going to see that this is equal to what we call the conjugate, convex conjugate of fi, evaluated at ai times v. And we write that as fi star of ai times v. That's just exactly what this is here. It's this we call the convex conjugate, plus bv. Right, it's just actually the negative conjugate. So for many instances, we'll be able to form this function. And the dual problem now is to maximize the sum of fi star of ai times v plus bv. Well, first of all, there's only one variable, v, so that makes it easier. Second of all, we've gotten rid of this kind of complicating constraint in the primal. Right? We've decoupled it. This now gets kind of, like I said, moved into the. We can think of the criterion here as a sum of two things. This part in an indicator that tells us that A transpose X equals B. We've essentially moved the linear transformation from the indicator up into the part involving F. It's our first example of something called dual decomposition. So this is the dual problem, to maximize this quantity. Equivalently, right, maximizing g of v over all v is the same as minimizing over all v negative g of v, right? So we can write that as minimize fi star and one property we'll learn about the convex conjugate is that the convex conjugate of any function is always convex. So it's nice. Actually, that shouldn't have surprised us here because we know that dual problems are always convex. So regardless of what we knew about the convex conjugate, we know that whatever comes out of here has to be a convex function because dual problems are always convex optimization problems. And let's suppose we actually managed to solve this. Suppose we solved it, and the solution was v star. Then we can get back the primal solution by the stationarity condition. The stationarity condition tells us that if we were to plug that back into the Lagrangian, which is this, then the primal solution has to minimize the Lagrangian when I plug in v star. So what would that mean if I told you that x minimized this quantity when I plug in v star? Well, again, that's just determining x individually in n different components, right? Because each component of x only appears in one term. So then from this we can get the primal solution by solving the following equation. We want to minimize this term over all xi, right? If we could do that for each I, then we're going to have minimized the Lagrangian over x. And we do that by taking its gradient and set it equal to 0, for example. I told you this, that fi was differentiable, assuming it's convex. So we have to solve this equation for every I. So if we can solve that, then we get back the primal solution. In many cases, if you know a function's conjugate, we have lots of instances. We'll learn shortly that we know it's, so if you know the function and it has some kind of, lies in some problem class, lies in some form of functions, we know it's conjugate in closed form, we can solve this as well. So we'll see many instances in which all this is very tractable. I just wanted to give you the general principle with an example like this. Any questions about that?
Will you give an example of F star?
We'll see lots. For example, if f is a quadratic, f star is also quadratic. So quadratics have quadratic conjugates. We know the conjugates of norms. We know the conjugates of lots of functions, like functions involving logs, exponentials. So we'll see lots of examples of that. Conjugate's really just shorthand notation. It's a, if you didn't know anything about conjugates, you could still derive the dual. You just would go through the steps manually. The conjugate is another way of kind of abstracting out things that you know so that you can piece together dual problems easily. That's really what it does. But we'll see that. That's what we're going to spend a lot of time on this lecture. Other questions? Okay, how do I solve, I want to ask another question. How do I solve this one-dimensional minimization problem? How would you solve it in practice? What's your algorithm for it? When it gets down to one dimension, you don't need to know anything fancy. That's the point I wanted to get across. I would divide the domain into 1,000 discrete points, and I just try all of them. Something like that. I mean, one-dimensional minimization is not difficult. If the problem's convex or non-convex, it doesn't matter. When you get down to one dimension, you can pretty much just discretize the function and see what point on your grid achieves the smallest function value. And then you can go in a neighborhood of that and do it again if you want to make it more accurate. But there are some more fancy methods for one-dimensional minimization, but I don't think that they're really that relevant, right? Like, it's important to learn algorithms for minimization when we talk about Rn, but in one dimension, you could do pretty much one of many very basic things, and you'd be fine. Okay, so today we're going to talk about, these are some of the correspondences and uses of duality. The first thing we'll start on is dual norms. Just kind of review that. Then we're going to talk about conjugate functions. That'll form most of the meat for today's lecture. And we'll talk about dual cones, which is useful for conic programming. And lastly, I want to make sure I get to this, some dual tricks and subtleties. So some tricks that you should know about when you're going to derive dual problems. There are lots of other uses of duality and relationships with duality that we could discuss. There's not enough time. Duality is kind of I think it's a concept that it exists and is pretty ubiquitous across many different fields. So and they're all kind of related. It's very beautiful. So the duality that you learned if you studied analysis is very related to this type of duality. Duality in convex geometry, which we're not going to talk much about, is very related to this. So they're all kind of related in some way. So I think it's a very beautiful topic. So dual norms, let's just come back to these and review them. Let's suppose that x is a norm. So I'm using just 2 bars to denote an arbitrary norm. There's no subscript here. Examples of norms that we care about, for example, commonly are like the LP norms, which are convex when p is bigger than or equal to 1. You've learned those. The trace norm, which is you take a matrix and you sum its singular values. So R is the rank of the matrix here. The dual norm of any norm is defined by the following maximization. So we write it as the usual norm notation, and then we use a subscript star here to note that this is the dual of the norm that just is kind of in the plain norm notation with no subscript. We look at the maximum inner product with x over all vectors z that are in the unit ball defined by the original norm. That's how a dual norm is defined. This immediately gives us the inequality that if I take z transpose x and look at its absolute value, then in any norm that's less than or equal to the original norm, z, times its dual norm of x. So this is like Cauchy-Schwarz, right? What does Cauchy-Schwarz do? It usually tells us that z transpose x is less than or equal to the L2 norm of z times the L2 norm of x. But we're going to see that the L2 norm is self-dual. It's just an example of, so it's just an example of this, this inequality. This is sometimes called Holder's inequality when it's mentioned for LP norms. You might have heard that called before. Why is that true here? Can anybody see why that's true from this definition? Let's just start off with z transpose x. How can I bound this? Well, first of all, if they give me any z transpose x, I can always write that as the norm of z times z transpose x, or I could write z over its norm transpose x, as long as z doesn't have norm 0. But if z has norm 0, then both sides are 0 here, so it doesn't matter. And this is now equal to z times it's less than or equal to z times the maximum, say, over all w that have norm less than or equal to 1 of w transpose x, right? Because this is just one example of such a w, so it's going to be certainly smaller than or equal to what happens if I take the maximum over all w. And this, in turn, is equal to the dual norm of x. That's how we define it, right? So it's just very simple. Comes right from the definition of the dual norm. The other direction is similar. I'll let you guys work that one out yourselves. So what are some dual norms that we know? These are things just to remember. Proving that these are dual norms is actually not incredibly difficult, but it is itself an exercise. So it would be like something that we might put on a homework. The dual norm of the LP norm is an LQ norm, where if P is larger than 1, then so is Q. And P and Q are what's called complementary, or they're also just called dual. They satisfy 1 over P plus 1 over Q equals 1. So for example, if I had the L2 norm, then its dual would be the LQ norm, where Q satisfies 1 over 2 plus 1 over Q equals 1. But that means that Q is 2. So the L2 norm is what's called self-dual. It is its own dual norm. And that gives us back the Cauchy-Schwarz inequality you already know. What's the dual of the L1 norm? It's the infinity norm, right? So again, the dual of the L1 norm is the LQ norm that satisfies 1 over 1 plus 1 over Q equals 1. Q must be infinity there to make that work. And likewise, the dual of the LQ norm is the L1 norm. The trace norm dual, the dual of the trace norm is the operator norm. So that's another very useful relationship. If I ask for the dual of the norm that takes the sum of the singular values of a matrix, its dual is the norm that returns me the largest singular value. Again, this is not it's not something that I think is necessarily intuitive, but it's certainly something that you could prove if you were asked to. So these are things I would say just to remember. They're very useful relationships. Lastly, the dual of a dual norm, we can show that, and this is the kind of thing that you should think about how to show. It's similar to what you're doing on your homework. On your homework, you're showing that the conjugate of a function is the original function. It's a pretty similar exercise here. The dual of the dual norm is the original norm. Okay, so that's, for example, how we might know that the dual of the L infinity norm is the L1 norm if we knew that the dual of the L1 norm is the L infinity norm. I mean, they're both easy to show, but then from this fact, you also know that the dual of the operator norm is the trace norm. So it goes both ways. That's all this is saying. Questions? So we'll see how dual norms pop up in duality when we look at conjugate functions coming next. Okay, conjugate functions, I would summarize by saying they are a useful mathematical formality that aids us in deriving dual problems. It's a shortcut to remembering how to derive certain dual problems. If you didn't know conjugates, like I said before, you would still be able to derive dual problems just the same, because there's nothing really new that comes out of conjugates. It's just like when we learn convexity, we learn tricks like operations that preserve convexity. Again, that didn't necessarily tell us something that was new. We could have probably derived, albeit arduously, those operations that preserve convexity from the rules of convexity, but it just it enabled us to call things convex or not convex more quickly. Same here. Conjugates enable us to derive dual problems more quickly. It's a good thing to have in your toolbox. So the conjugate's very simple to define. If you give me some function, then its conjugate is defined as follows. We denote it by f star, if f is the original function, and it lives on the same space as f does. So if f lives on Rn, then so does its conjugate, f star. It's what we get by maximizing over all x, y transpose x minus f of x. It's a definition of a conjugate function. So this is how you define the conjugate at y. First thing to notice, this is always a convex function. Why is that true? Well, what do these look like as functions of y? Right? We can write the conjugate as f star of y equals the maximum over all x of some function g of y indexed by x. Right? And g sub x of y, we know is just equal to y transpose x minus f of x. So what does this function look like as a function of y? What kind of function is it as a function of y? It's just linear. It's affine, actually. So I'm taking a maximum of affine functions of y. I'm taking an infinite maximum of them, but it doesn't matter, because a maximum of convex functions, no matter how many things I'm taking the maximum over, is always convex. So that means that this is always convex, right? Because affine functions are convex, so I'm taking a maximum over convex functions. So that's analogous to what we learned in duality, which is that the dual problem of any problem is always a convex problem. Analogously, the conjugate of any function is always a convex function, even if the original function wasn't convex. Okay, so for a differentiable function, you might have seen this in another class called the Legendre transform, something that you learn. I think people often learn that in physics, for example. So what are some properties of the conjugate function? Why do we care about it? Well, it has a lot of nice properties, and we also can use our knowledge of conjugates of kind of known functions to build up conjugates of larger sums of functions, for example, or compositions of functions. That ends up being very useful in deriving duals. So here are some of the properties of conjugate functions. The first is called Fenchel's inequality, and it tells us that for any x and y, f of x plus f star of y is always bigger than or equal to x transpose y. I think, if I'm not mistaken, you're proving every one of these things on homework 3, except for maybe the last one, but it's very straightforward. So that's where the proof comes from. It comes from your homework 3. We could talk through this first one. I think this is one you guys can all see. How would I prove this first one? Right, this is saying that f star of y has to be bigger than or equal to y transpose x minus f of x. For any x, why is that true? Well, what's the definition of f star of y? It's the maximum of that over all x. So clearly it's going to be true for any x, right? So that first property is immediate. The conjugate of the conjugate satisfies f star star is less than or equal to f. So this means pointwise. If I evaluate this at any point x, it's always less than or equal to this at any point x. If f is closed and convex, then I can take the conjugate twice and I get back the original function. It's analogous to what happens with the dual norm here. So if I had a closed and convex function, then the conjugate of the conjugate is the original function. That one, I think you're proving, that might be the most difficult thing to prove in the homework. But it's outlined in the homework for you how to do it. Here's a very useful one. If f is closed and convex, then I can characterize subgradients of the conjugate of f via subgradients of f. So x is a subgradient of f star at y, if and only if y is a subgradient of f at x. This is an equivalence for closed convex functions. This one you're going to prove in 2 steps in the homework. And that in turn is equivalent to the following fact, that Fenchel's inequality is tight. So for closed and convex functions, if we have x being a subgradient of f star of y, that's equivalent to y being a subgradient of f at x, which is in turn equivalent to f of x plus f star of y being equal to x transpose y. And when we talk about dual decomposition later, it's all going to rely on these 3 equivalences. You'll see when we derive, for example, the method of multipliers or ADMM later in the course. Lastly, convex conjugates have kind of simple calculus properties, just like convex functions do. One of them is that if I have a function which decomposes into a sum of 2 functions on non-overlapping blocks of variables, if fu of v is f1 of u plus f2 of v, then the conjugate splits up as well. F star of, say, w comma z is f1 star of w plus f2 star of z, where f1 star is the conjugate of f1 and f2 star is the conjugate of f2. Okay, let's get to some examples. I think that's going to help us. Understand conjugates a little better. So let's deal with a quadratic first. So let's suppose that f of x is 1/2 x transpose qx, where q is positive, definite, strictly, which means that f is a convex function, strictly convex function. Then the conjugate, right, is given by maximizing over all x, y transpose x minus 1/2 x transpose qx. That's maximizing a strictly concave function, right? So we know how to do that because this was convex. We can also write that, if we just want to be more comfortable, as minus the minimum of 1/2 x transpose qx minus y transpose x. What's the minimizer here? It's a minimizing value of x. This is what I said you guys would tattoo to your arm. Or maybe I said that about the gradient of the least squares loss. I can't remember. But both of these are things that you should internalize, because we're going to, quadratics are kind of at the center of a lot of this. Take the gradient, set it equal to 0 here. It's just q inverse times y, right? So it's what I'm going to plug in q inverse times y in for x, because that's the minimizer. And I see that I get minus 1/2 y transpose q inverse y. Sorry, there's no minus there. Minus y transpose q inverse y. So the whole thing is just equal to 1/2 y transpose q inverse y. So if f is a quadratic, convex quadratic with strictly positive definite q, its conjugate is a quadratic in the inverse of q. Okay, this is again a strictly convex function, because if q is positive definite, then so is q inverse. Right? So that's an example of a conjugate. Fenchel's inequality, right, if we apply it to this, is going to give us the following fact. If I take any positive definite q, 1/2 x transpose qx plus 1/2 y transpose q inverse y is bigger than or equal to x transpose y. That was a trivial inequality to derive from the properties of conjugates, but it may not have been one that you know already. Maybe a pretty non-trivial inequality when it comes to quadratics. How about another one? Let's try the indicator function. There's not much to do here, right? Because for indicator functions, if I have f of x being the indicator of being in some, say, set C, then its conjugate is just equal to the maximum over all x of y transpose x minus the indicator function. This is going to be equal to negative infinity when x is outside of the set C. So really this is just the maximum, and it's 0 otherwise, over all x in C of y transpose x. So that's not closed form, but that's about as good as we're going to get for just a generic indicator function. This is called the support function of the convex set C, if we start with the indicator function. Okay, both of these functions are closed and convex. Actually, this is closed and convex if C is closed and convex, which means that since we derived the conjugates one way, we know that we also have the other way. So if I asked you what the conjugate of this was, it would be that. And if I asked you what the conjugate of the support function was, it would be the indicator. Right, just from this last property, or the third property here. F star star equals F. Please ask questions if you're not following. This is another one of those things which the arguments aren't complicated, but it's something that's a bit subtle. So I would like to know if you guys have questions. Okay. Okay, so it's going to keep plugging along. We're going to get through the end of these examples, and then we're going to apply this to derive our first dual problem using conjugates. So how about a norm? If I were to tell you that I had f of x equals just some arbitrary norm, say the L2 norm for concreteness, then its conjugate is the indicator function of its dual norm ball. It's kind of a mouthful, but it's something that I don't think is too hard to remember. So if I have this being the norm of x, then this is the indicator function of y being in this set of all points that have dual norm less than or equal to 1. So I guess I could write that like this. Okay, I actually claim that this is not new. We could have gotten this from our last fact. How do we get this from our last fact? Let's connect a few of the pieces we've learned so far. F of x is a norm. What's another way of writing f of x for a norm? Hint, I claim this is the dual of something. This norm is the dual norm of something. What is it the dual norm of? The norm star, right? Because the dual of the dual is the original norm. So I can always write this as the maximum over all z that have dual norm less than or equal to 1 of z transpose x. It's an alternative representation for the norm of x. Because this is, right, this guy is equal to the dual of the dual norm, which is the original norm. Another way of expressing just the norm of x. What is this guy here? This is the support function. It's the support function of what? Of this set. The set of all z for which the dual norm of z is less than or equal to 1. What's the conjugate of the support function? Well, we just learned that from the last slide. Right? We learned that the indicator function has conjugate equal to the support function, so vice versa. The conjugate function the support function's conjugate is the indicator function. So therefore, we already know that from the last slide. F star of say y is going to be the indicator function of whatever this is. Okay, so that was an example of how we used the last fact to prove this. Here's another proof that I give on the slide. This is from first principles. So it tries to tell you, just argue for you directly that this is the conjugate. So you can go through that if you're curious. Another shorter way to see it is this argument I gave right here on the notes. So keep in mind, for example, if my norm is the L2 norm, then its conjugate is the indicator that y has L2 norm less than or equal to 1. If my norm is the trace norm, then its conjugate is the indicator that the operator norm of my matrix is less than or equal to 1. So it's the indicator that my matrix has its largest singular value less than or equal to 1. Okay, so we know how to derive now conjugates for, say, quadratics, norms, indicator functions. There's a lot more we can do. You're going to do a couple more in your homework as well. But these are just some examples. Okay, let's use them in our first dual problem, and then you're going to see why they're useful and how they come up. So let's try to derive the lasso dual. We already did the SVM dual a couple lectures ago. Yeah, Dels. So the conjugate of a norm is not a norm. It's an indicator that the norm of its argument is less than or equal to 1. But the dual norm is always a norm. It's just it's more convenient to think of the dual of a norm being a norm, I guess. It's a good question. So let's derive the lasso dual. Like I said, we already saw the SVM dual. Let's do it for another kind of common problem that we might look at it in stat and ML. We're going to see a couple things actually in this example. The first thing we'll see is the first dual trick, and the second thing we'll see is the use of conjugates. So here's the lasso problem. What happens if I asked you to derive its dual? What's its dual function? I'm curious to know what's its dual function. How many variables does the dual function take? What's its dimension? It's kind of tricky, right? There are no constraints here. Dual function is a function of no variables. It's just a constant. And it's equal to the minimum of this over all x. Right? It's defined as the minimum of the Lagrangian, which is the criterion plus the Lagrange multipliers times the constraints. There are no constraints. That second term, the Lagrange multipliers of dual variables times constraints is 0 because there are no constraints. So it's equal to the minimizer of the criterion, which means it's just f star. Completely useless, right? If I were to ask you to derive the dual here, there's nothing to do really. So people might think that we're stuck here. Here's our first dual trick. We're going to introduce some auxiliary variables. Just create fake constraints. That'll give us dual variables that are not trivial, vacuous, and we'll be able to derive a dual. So you can do this in more than one way. Let's rewrite it in the following way. It's equivalent to minimizing over y minus z squared plus lambda times the L1 norm of beta subject to x beta equals z. Didn't change the problem, didn't help me to solve it. It was kind of a trivial rewriting, but it's going to help me derive the dual. So I've introduced this constraint now. Now the Lagrangian is what? The Lagrangian is a function of our primal variables, which in this case are z and beta, and a dual variable, which I guess I'll write as v. I guess I called it u on the slides. It's just the criterion plus u transpose z minus x beta. So let's minimize that over all z and beta to get the dual function, which will be a function of u. So I want to minimize the Lagrangian over all z and beta. Let's break that up into minimum over all z plus a minimum over all beta. We'll see we can actually do that. So what are all the terms involving z here? It's just this guy and this guy. So what is that? It's a quadratic. We can do that one, no problem. We'll come back to that. Plus the minimum over all beta of something. And that looks like this. Lambda times the L1 norm of beta minus x transpose u transpose beta. So I've just split it up into two separate minimizations because it can be decoupled that way. Let's see. This first one is an exercise that actually is very similar to what we did for the conjugate of a quadratic function. In fact, if you think about it for a second, it's really identical. We can rearrange this if we want to make it look like the conjugate of something, but in this case, it's easier just to actually approach this directly. If I asked you to minimize this over all z, you would hopefully know what to do, right? Which is, I would just take its gradient, set it equal to 0, and then remember that magical rule. And the minimizer here is going to be y minus u, right? And so Yeah, that's right. And so if I plug that in, then I'm going to get the following, which is 1/2 the norm of or I guess, no, sorry, it's u minus y. So I get 1/2 the norm of y squared minus 1/2 the norm of y minus u squared. So do that calculation in a few more steps if you're not sure about it. This is the minimizer of this over all z. And let's look at the second one. So this one we just did directly. The second one might be tricky because it involves the L1 norm, which is not differentiable. We might think we have to write down subgradients, go to some lengths to figure this out. But this is where our knowledge of conjugates is going to come in useful. Let's rewrite this as minus, so instead of saying plus the minimum, I'm going to write this as minus the maximum of what's inside. To make it more like a conjugate. And in fact, I'm actually also going to pull out lambda. So it's minus the maximum of negative what's inside. So that's x transpose u over lambda transpose beta minus the 1 norm of beta. Just rearrange that. What is this if I maximize overall beta? What does this remind you of? It's the conjugate of the L1 norm, evaluated at what point? Evaluated at this point. X transpose u over lambda. This is actually a general principle. We're going to see that conjugates in dual problems are like best friends. Conjugates always appear in dual problems. So we didn't have to actually go through this. We can just recall this is the conjugate of the 1 norm evaluated at this point, x transpose u over lambda. And so the dual function is equal to 1/2 y squared minus 1/2 y minus u squared minus lambda times this, which is the conjugate of the 1 norm evaluated at this point, which we know is the indicator of this point having infinity norm less than or equal to 1. The conjugate of the 1 norm is the indicator that its dual norm is less than or equal to 1. And I got rid of the lambda because this is either going to be 0 or infinity, so it doesn't matter that I was multiplying it by lambda. And I'm also just going to, for the sake of rearranging, I'll just multiply through by lambda and say this is the indicator that x transpose u in infinity norm is less than or equal to lambda. So this is g of u. And therefore, the lasso dual is to maximize this overall u, which is the same as, let's just get rid of a few things. I don't need to worry about this because I'm talking about a maximum over u, so it's equivalent to minimizing, say, 1/2 y minus u squared plus this indicator, but I'm going to write that as a constraint. That's all this ends up adding as a constraint. So there we go. We derived the lasso dual. We didn't have to do much work either, right? This is the lasso dual. That's the lasso's original problem. Questions about that derivation? It was easy in a sense because we used this conjugate trick here. That part would have been hard if we didn't have that trick. It wouldn't have been impossible. We could have done this with subgradients. I'm just saying it would have been more laborious. I don't actually have my watch, so I don't know what time it is. Okay, let's take a quick break, couple-minute break, and then we'll come back and we'll finish off duality uses and correspondences. So let's finish up a few more comments about the lasso dual, and then we'll just talk about the role of conjugates in dual problems more generally. So what do? Right? We wrote down the lasso. It's Lagrangian after introducing a constraint, minimize it to get the Lagrange dual function. Strictly speaking, we ended up with this problem. maximizing the Lagrange dual function. This constraint came from the fact that the Lagrange dual function actually had an indicator in it, right? That would make this, it's the same as writing on this constraint. It's equivalent to minimizing the negative of this criterion and throwing away terms that don't depend on the dual variable u. So it's equivalent to this problem. So let's think about one of the first points we made, which was that we can often get primal solutions from dual solutions. Let's come back to that. So let's see what happens here. Does strong duality hold here? It does, right? Because if we go back to the primal problem, what's the one we have to look at, actually? We have to look at this problem. Because this was the problem whose dual we took, this kind of fake constraint z. So we're asking about, does strong duality hold between this problem and its dual? Of course, this is equivalent to that. So it's really the same question we're asking about this. But looking at this problem, it's convex, clearly, and it's clearly feasible. Right? All I have to do is find z and beta such that z equals x beta. For example, putting both 0 there makes that feasible. So Slater's condition hold, and we have strong duality, which means that the Lasso's dual attains the same objective value as the Lasso's primal does. But let's be careful. That means that if I were to maximize this over all u, then g star, that value, would be equal to f star, which is the optimal value of the Lasso criterion. That's not saying that if I were to look at the minimum over all u of this problem, then that criterion value would be equal to f star, right? Because I've actually transformed the dual. I've done a few things to it. I've gotten rid of this constant term, and I've flipped the sign of its criterion. So it's a mistake people might make is you might think, this is the Lasso dual, and then you'll implement something, and you'll check the duality gap by subtracting off the Lasso criterion value at beta from the criterion value of this at u. But that's not the real duality gap. This is not the actual dual problem that we know achieves the Lasso criterion value optimality, right? Because it's just a transformed version of the dual. Of course, it's perfectly appropriate to solve this and claim that the optimal u here is the same as the optimal u here, but I'm just trying to say the obvious point that they don't have the same criterion values at optimality. So just be careful you don't forget about that. Because very often you'll derive a dual and then you'll make it simpler by getting rid of constant terms and maybe flipping its sign or whatever else you want to do. But all those things are going to affect it's not going to affect the solution, but they'll affect the dual criterion optimality. How about the thing we care about more, which is how do we get a Lasso solution from the dual solution? That might be of interest to us. Suppose we knew how to solve this, and we don't know how to solve the Lasso. How could we get the Lasso solution? Well, we go back to the Lagrangian. So let's write down the Lagrangian. Right, which was L of z beta u equals 1/2 y minus z squared plus L1 norm of beta plus u transpose z minus x beta. If we were to plug in the optimal dual solution here, then both beta and z are characterized by minimizing this. Let's look at the minimizer over z first. We actually already computed that. So the minimum over z, the minimizer over z, is z equals y minus u. If we were to minimize that over z, you'd see that it's just given by y minus u. At optimality, though, z and x beta are the same, though, right? So that's the same thing as saying that x beta is y minus u. Because at the solution, these two are the same. It's the constraint we introduced. So therefore, the Lasso fit, the fitted value from the Lasso, is given by the residual in the dual. There you have it. That's the characterization for the Lasso fit, the prediction we'd make in terms of the dual solution. So I want to say just a few things. I don't want to take too long because we're a little bit behind on the rest of the lecture. But I wanted to make a few points for those of you that are interested in using the dual for kind of some statistical characterizations, because part of what I said was that the dual is not only useful for understanding a problem, for solving a problem, it's also using for understanding a problem and its properties. And here's an example of where this comes into play. Let's take a look at the dual problem here. Right, I've just rewritten it as minimize y minus u squared, subject to u being in some set C, and C is a set of all u for which x transpose u is infinity norm less than or equal to lambda. Just rewritten it, nothing fancy there. Forget about this next line for now. What is the solution to this problem? Not in closed form, but what is this problem asking for? We have some set C. I actually claim it's a polyhedron, and that's what this next line was showing. That's C. And the dual solution is given by projecting y onto C. Right? It's the minimum of y minus u in L2 norm subject to u lying in the set C. That's just projection onto C. We've already talked about that a bit. Furthermore, I claim this is actually a polyhedron. The set C is a polyhedron. You can see that in one of many ways. You can write this as an intersection of a bunch of half spaces, for example. And this is another way of seeing it, what I wrote down here. Okay, so now we have this nice picture in the dual. What is the primal solution? From our calculation with the Lagrangian, the primal is actually just the residual from this projection. So it's y minus u. It's this vector, the residual. The primal is given by the residual of projecting y onto the set C. So this can be used in actually a lot of ways by using some pretty simple geometry to make statements about the Lasso problem. And this has been done in a few papers, for example. What's one thing we can get immediately out of this? Here's a pretty non-trivial fact we can get from it. I claim this actually shows that the Lasso solution, x beta hat, is Lipschitz continuous as a function of y. So I claim this implies that at the solution, x beta, I guess I'll write x beta hat y, just to be clear, it's the solution, is Lipschitz continuous in y with Lipschitz constant L equals 1. It's a very strong form of Lipschitz continuous. It's non-expansive. How do I see that? Well, here's a simple fact about projection onto convex sets. If I were to project y onto a convex set, and I were to project y prime onto a convex set, some other vector, then the distance between their projections is no bigger than the distance between y prime and y. It's a property of convex sets. Projection is non-expansive. You can see that wouldn't be true with non-convex sets, right? Draw yourself an example where that's not true. It's a pretty simple fact about projection onto convex sets. It's also true about the residual from projection onto convex sets. The residual is non-expansive. QED, because x beta is the residual from projecting onto a convex set. So this comes directly from what we know about some kind of simple problems, simple properties of convex sets, some simple convex geometry. On the other hand, that's a very non-trivial property to establish analytically, right? It may be interesting to say that if I asked you to solve the Lasso problem at y and at y prime, some perturbation of the response, then I don't expect them to deviate any more than y did from y prime. It's a pretty nice stability property of the Lasso. It's also not something that's maybe you would think is easy to do from first principles. But here it comes from the dual. Just check the time. Okay, so we have a few minutes left. Let me tell you about conjugates and dual problems. This is the most important point. We're going to skip the dual cone stuff. It's not as important. So conjugates pop up all the time in the derivation of dual problems because the negative conjugate of f is equal to the minimum over all x of f of x minus u transpose x. This is just given by taking the negative sign on each side of the equality that's defining conjugates. And this looks a lot like what we do in minimizing the Lagrangian, right? We have some part of the criterion function, and we subtract off the Lagrange multiplier times something, if that something's involved in the constraint. So here's an example. If I asked you to minimize f of x plus g of x and I want you to derive the dual for this, the dual problem can be expressed succinctly in terms of the conjugates of these two functions. And the answer is the maximum overall u of negative f star of u minus g star of minus u. So it may be easier to think about an equivalence dual, which is just minimize overall u f star of u plus g star of minus u. So that's the dual of this problem. The arguments for that are very simple. They just come from introducing a fake constraint, like we did with the lasso dual, and using the definition of conjugates. So go through that slide, write it down to make sure you understand it. We're going to skip through it because we're short on time. But there's no trickery here. It comes directly from the definition of conjugates. So if you knew the conjugate of one of your functions, you knew the conjugate of your other functions, the dual is just by given by adding their conjugates together. That'll help save you a lot of time. On the homework, you're going to prove a slightly more complex version of this where you have a linear transformation inside one of the functions, and you'll see that what I said earlier is true. That linear transformation then moves inside of the other function in the dual. So you can kind of interchange the role of the linear transformation between the primal and the dual. Dual cones, we're going to skip. You don't need to worry about that part. This is, I want to just repeat this because it's important. Oftentimes we're going to derive a dual, and we'll end up at something, and we'll simplify that dual by transforming it, getting rid of constants, subtracting off things, changing the sign of things by making it a maximum, minimum, etc. But the warning is that if you were to go forth with that dual problem from then on, even under strong duality, the optimal value of that dual problem is likely not going to equal the optimal value of the primal if you've made transformations. Right? It's really the original dual problem's criterion. It doesn't hurt you in terms of solving it, but just don't incorrectly calculate the duality gap based on a transformed dual problem. A common trick for deriving duals we've seen is to introduce dummy variables, auxiliary variables. We'll do this with ADMM as well. If you don't know how to derive a dual for an unconstrained problem, or even for a constrained problem, if it's hard to derive the dual, a very common trick is to introduce a constraint, an equality constraint, which just kind of duplicates the variable but makes the minimization of the Lagrangian simpler. So there's actually some ambiguity in how to do that. With the lasso problem, remember I introduced the constraint z equals x beta. I put in z equals x beta here. If I actually decided to make z equals beta, that would have been fine too. Or if I decided to change this beta into something, that would have been fine too. But you'll see I actually get different dual problems. They're all equivalent, but I get different dual problems with each one of those substitutions. Well, actually, the latter two end up being equivalent, but they're both different from what I get here. Even though they have the same solution, they're different. And that ambiguity is actually maybe both hurtful and helpful. It's hurtful because it may seem like there's too many possibilities when you write down a problem into how to introduce these constraints. It's helpful in that there's not usually that many possibilities, so you can think about each one. And often these dual problems will have different strengths in terms of how tractable they are. So I like this one, for example, because in this one, in the dual, there's no inverse of x. It doesn't involve inverting a matrix. You'll see that if you introduce z equals beta here, then in the dual, you'll get the inverse of x appear in the criterion value. I didn't like that because actually computationally that might be more difficult to deal with. But that other dual problem is easier in a sense because if you go to its final form, you see that there's not a linear transformation that's kind of composed with a constraint. So they each have their own strengths. So just a note, when you go to derive dual problems, there's different ways to do that. So that's the end of our time today. We didn't get to the convex cone stuff, dual cone stuff, and the double dual stuff. This is a question I get asked every year, so I've started putting it in the slides. I'll just end by saying that very often, if you derive the dual of the dual, you get back the primal. So there's no infinite loop here of wisdom. You can't really just keep driving duals to get more out of the problem. Doesn't always happen. There's actually some exceptions where the dual of the dual is actually interesting and different than the primal, but most often it's the same. So you might have thought to try that, but you won't get much out of it. Okay, that was the end of our unit on duality. We'll start on Newton's method next week, and I'll see you then.